Now we're going to consider damping. Damping is what causes things like this oscillating mass to eventually stop oscillating. So damping is caused by forces which resist the motion, such as friction and air resistance. A common equation that we use to describe damping is F is equal to minus BV. This is an approximate equation and it tells us that the damping is proportional to the speed and directed in the opposite direction to the speed, which is common for things such as air resistance. So if we consider the spring, we know that the forces on the spring can be described with Hooke's law minus kx. So if we include this damping force, we've got that our total force is equal to minus kx minus bv. Now this is quite a complicated equation and you wouldn't be expected to be able to solve it. But if you're interested, how we can solve it is we can write this out from Newton's second law. We know that the total force is equal to ma, which is the second derivative of the displacement. So we could rewrite this equation as m d squared x dt squared is equal to minus kx minus b dx dt, because the velocity, the v, can just be written as dx dt. A way to solve this is using the solution x is equal to a, where a stands for the amplitude, e to the power of minus b on 2m, or times t, times cos omega t plus phi. So if you're keen on maths, you can substitute that in and show that it is indeed a solution to the equation that we've just given. Okay, but overall what this equation tells us is we've got that a e to the minus b on 2m times t out the front of our cos term. So our cos term is just the normal simple harmonic motion term which describes how the mass goes up and down, up and down, up and down. And the a to e to the minus b on 2mt is the amplitude term. And as t gets bigger, then we're doing a times e to the minus a big number, and that means that we've got a really small number. So this part out the front tells us how the amplitude slowly drops off with time. So we're multiplying this exponential drop off by the cos function, which is going up and down, up and down, up and down. So you can see here the result of that. So we've got an oscillation going up and down, up and down, up and down, but it's also dropping off. But we also have to actually change omega a little bit. For our normal simple harmonic motion without the damping, we had omega was equal to the square root of k on m, which is just the natural frequency for the spring. It's the frequency that the spring wants to oscillate at. When we include the damping, it's complicated, but we actually end up with something with an equation omega is equal to the square root of k on m minus b over 2m all squared. Now what's interesting with this thing is that we can actually imagine a case where we have really big damping. So imagine maybe if I submerged this in honey, so now there's even more force resisting the motion. And in that case we could come up with a case where k on m was equal to b over 2m squared, and that would mean that our omega was equal to 0. So in this case it's known as a critically damped case, because when we times it, we now don't have any of those oscillations going up and down, up and down, up and down, because our omega is now 0. So that cos term is just a constant. In this case, cos of 0 is equal to 1. And so all the motion is described by that x equals a e to the minus b on 2m times t. So that case is known as critically damped. But that's not the absolute limit to the damping. We could ramp up the damping even further. So now we've got a really big force which is trying to stop this moving. And in that case, it's known as overdamped, and the result is that it returns to its equilibrium position even slower because there's even more force trying to stop it returning to that equilibrium position. So by now you can probably see that the amplitude of the spring that we started springing at the start of this video has decreased quite a bit from what it was initially. Now this doesn't just apply to springs. We've been using a spring because that's a nice simple case, and even though the maths looks complicated, it's a lot less complicated than the other situations we could consider. But it also works in musical instruments. So with this guitar, if I pluck a string, damping causes the sound to slowly decrease as the oscillations in that string slowly die away. So we've considered it in terms of forces. We can also think about it in terms of energy. When we have damping present, the forces are doing work, and this work is taking energy out of the system. So in this case, we were losing energy because of the work done overcoming the air resistance, and here we were also doing work and losing energy from the system, which is what allows those oscillations to die away with time.